All right, you good? We're good. OK, so let's keep on going with the theme of hardware vulnerabilities. This time, I'm going to be talking about some fault attacks and just a little bit of side channels. So I'm Sébastien. This work was done as part of my PhD, so the co-authors are my advisors. All right, so I'm going to jump straight into it with some fault attacks. OK, so fault attacks is all kinds of attacks where you disrupt the hardware on purpose. Sorry. Oh, my bad. Thank you. We disrupt the hardware on purpose in order to create incorrect executions. These are very powerful attacks. Anything that can break will break. You can have instructions getting skipped, cache entries being corrupted, math being incorrect. Anything can happen. But when you look at this in a principled manner, there are still countermeasures that you can use to make the attacks more difficult, and some of them rely on software. And when they do, typically, because of the low-level nature of the attack, they require software to use very precise assembly code with non-functional purposes. And non-functional things can be computing the same value multiple times, double-checking your control flow, cleaning up secrets after use, and so on and so forth. Now, I don't need to tell you, but I will tell you anyway, that if you try to run this kind of code through a compiler, the compiler will ruin your day. So here's an example. Because the main problem is it's all semantically unnecessary. And we've seen the memset example before. If you write memset like this to memset an array that you're done using, the store is dead, and therefore the program is semantically equivalent to nothing. And compilers like to output nothing. If a compiler can output nothing, it's the preferred option every single time. So what do we do? Well, what we do is kind of subtle, is we trick the compiler into not doing what it is legally entitled to do. Yeah, so what we do, we try to trick it into not realizing this is a memset. So what we do, we try to call memset to a function pointer. Yeah. Of course, semantically, this is a nothing burger, and the compiler calls the bluff and still generates nothing. Yeah. So what we can do, we can make the function pointer volatile. Magic keyword comes in, and suddenly it works. You get a function call. But if you look at the specification of the C programming language, what you realize is that this is actually equivalent semantically to reading the pointer but not calling it. So we still have problems, right? The status quo is that we make the compiler our enemy, and then we get subtle bugs if it's Tuesday and the compiler is smart. And also, we have no formal guarantees that it works, because we have formal guarantees that it shouldn't work. So how do we fix that? How do we try to make security code like this a feature of a compiler and not an accidental bug? So here's my question. How do we preserve and compile non-functional properties? And I'm interested in implementing it in LLVM. So the main idea here is to wrap the non-functional properties, the security primitives, in such a way that breaking them would constitute a semantic breakage. And then we can rely on the compiler's existing guarantees of semantic preservation to argue that security is preserved. And the idea behind this is that this avoids us having to change every single optimization to make sure that it respects our new security contract. Instead, this sort of wrapping will let us focus on the program's representation and the lower rings, which is more viable to work with. Now, I mentioned in LLVM, right? I'm not looking for the cleanest, most elegant theory here. I'm looking for the most executable result. And so there are two subtleties that come with using a production compiler like LLVM. The first one is that LLVM goes through a lot of stages in compiling programs. You get basically 4 or 5 different languages, depending on how you count. All of them have their own semantics. And so all of them have their own non-functional things. So the specification for your security properties will vary along the compilation chain, which is a bit harder to deal with. Another subtlety, which is to our advantage this time, is that LLVM doesn't really implement the specification of the C programming language in its purest form. It's predictable in many places, and it also has a lot of extensions that constrain the behavior of the compiler more than the spec requires. And relying on this, fair game. Anything that's maintained and that works is fine, and upstream LLVM definitely is. Right, so that's the pitch, that's the objective. Now, how do we deal with this? And this is the last component that I didn't explain in the title. Tracing LLVM, that's just a name. It's the name of the compiler extension that I work on, which is, you can think of it as a prototype secure compiler for this kind of security countermeasures. And since I might forget, this will lead you to the code, the docs, and the tests. Now, how do we make LLVM preserve and compile our security code? Two big ideas. First one is opacification. That's how we're going to hide things from the compiler in a semantically relevant way. The second is tracing. That's how we're going to connect the high-level source code with its annotations with the low-level codes where we actually want to transform the program for security. So I have one slide and one example for each of these. So let's start with opacification, right? I didn't come up with this. This is a key concept from the PhD thesis of Sun Tuanvu from a couple of years ago. And the idea goes like this. Let's say I have x equals 73, and I don't want the compiler to constantly propagate it. One way that I can hide the value 73 from the compiler is by processing it through an opacification function here. And the point of this function is that it's going to be the identity, so the semantics of the programs are unaffected, but we declare the function as implementation defined. So we tell the compiler it could be anything. And because of this, the compiler is forced to perform only optimizations that would be valid for all implementations of the functions. Otherwise, it's semantically incorrect. So for instance, the compiler cannot replace x with 73 because that would be invalid for the implementation of opacify that does +1. Right? So this is how we semantically wrap our compilation constraints. And it's a fairly natural idea, so I extended it in Tracing LLVM by adding primitives for opacifying computations, where you tell the compiler what values you're working with, but you don't tell it what you're computing. Addition, subtraction, multiplication, could be anything. And also one primitive for opacifying types that I won't be talking about too much. So yeah, opacification, how does that help us? Here's an example, right? One thing we like to do when we compile countermeasures for these kinds of attacks, we might have some kind of data that we want to keep track of, like, I don't know, the sandbox base address from this morning. And we want that to be in a single register because it's convenient. So we'd like to allocate all the Lagranges of a source variable to a single register. And so here's how we can do that. Ignore the first line for now. It's going to be clear in the next slide. It's int x. And we tell the compiler we're going to do something special with the writes to x. So then I have two writes, x equals 73, x equals 0. And normally, if you do that, the first write is dead, so it shouldn't occur. And the second write might occur in a different register because it's a new Lagrange. However, with opacification, what we can do is we can take these store instructions associated with the assignments and hide them from the compiler. And this little snippet here, I mean, not easy to read if you've never read LLVM IR, but basically this is a single instruction. This is the opacification instruction that I added. And it has this instruction, this store, hidden inside itself, which is not something that you're normally able to do with LLVM, but I was able to implement that using LLVM's internal API contracts. And so what this does is that the compiler is just a black box that takes the same parameters as before, but has no specified semantics. It could be any instruction. So the compiler cannot perform optimizations related to stores. And due to other side-effecting things, it cannot remove them either. So the opacification preserves all the stores with the right values in the right order. And then when we reach the backend, there is a register promotion pass that's added in Tracing LLVM just before register allocation, which allows us to promote the stack location to a register. And when we do that, we can choose that all of the live ranges go to the same register. So we end up here with 2 immediate loads into the same register, which means that the load of 0 indeed erases the load of 73, which would not be obvious from the semantics of the C program at the top. All right. That was opacification. Now let's talk about tracing. Tracing is the idea that the source code doesn't tell you everything you want to know about the program. There's a lot of work happening between the source code and the assembly code. That's called the compiler. And so what we want to do for security is we want to track aspects of the source code all the way down to assembly so that we can verify that things are correct or just even implement the transformations late. Basically, this tracing idea is like debug information. But unlike debug information, if an optimization threatens to render the debug info invalid, the tracing info invalid, then the optimizations will be blocked instead of destroying the debug info. So yeah, that's a guaranteed connection between the source and target code is the big idea. So that's a bit more exploratory. I still have no idea exactly what a good set of tracing primitives is for implementing security countermeasures. So right now in Tracing LLVM, I have two of them. One for tracing the data flow of values. It's almost always going to be used to trace secrets. So we've seen, I think, about 150 of them today. And then one for tracing writes, which is what was on the previous slide, where we can tell the compiler that all the assignments to an AL value should behave exactly as in the source code. It's a way to tell the compiler that the variable in the source code has to be a storage unit in the assembly code and not just an abstract notion of the mathematical value. All right, so how does that help us writing countermeasures? Well, let's go back to cleaning up things. Where's Pierrick? Yeah, there. Now, zeroing memory, something you would do with a function call, memset, or something similar. Zeroing variables, obviously, a bit more annoying. So here's the pitch. We want to clean up all the registers at the end of a function that have held sensitive data, or things that depend on sensitive data. And there's a few reasons you would do that, but mostly side-channel resistance. So here's how you do that in Tracing LLVM. A bit of a mouthful, but we can see that. Let's say I have two secrets that are global values, secret 1, secret 2. I use this annotation there. The bang is a type constructor, and then the attribute asks the compiler to trace the data flow of this variable. And this is just a way to tell the compiler that this is all secret. And then let's say I have a code that has written secret 1 plus secret 2, for instance. What I want in the assembly code is I'm going to have two loads of the two secrets in two different registers, A0 and A1. And then I'm going to return in A0, so I do the add with A0 as the target. But before I return, I want to wipe A1 to make sure that I return only the return value that was intended and no other secret-related things. And this works because asking the compiler to trace the data flow means that the compiler will maintain a sort of permanent state analysis through the entire compilation chain. And then when we reach the backend, we can just ask the compiler, hey, please tell me all of the registers that are traced. So you can see how we go from a traced C variable to a traced register in assembly. That's the core idea of tracing that connects the two languages. All right. The actual sort of benchmark on which I've evaluated all this is a verify pin function, the kind you've seen 1,000 times, where I stacked 4 simple countermeasures, 2 source countermeasures for data flow and control flow integrity, so doubling the loads from memory and some kind of checkpointing, and then 2 countermeasures at the assembly level, which is not putting sensitive data on the stack and zeroing registers at the end of the function. So I'm not going to go into more details in this, but basically what I claim is that I looked at the assembly code and it's secure, so basically it works. Yeah, I mean, the code would barely fit on the slide, but who cares? The big idea is that we managed to implement multiple countermeasures at different levels of abstractions while connecting the source and target codes, which even on an example of this scale is somewhat remarkable. And also, we can activate all optimizations and nothing happens because, again, opacifications provides us with semantic guarantees. All right, I want to conclude a bit quickly, but I will just show you this slide. I think secure compilers are a little less compelling if you don't have an actual binary that you can actually execute. So I want to pitch not just the ideas of Tracing LLVM, but the tools themselves. And so I feel obligated to be honest about the state of the code because you know what they say about research projects. So yeah, like many things presented today, this is a bit of a work in progress, but it's more than just a hacked demo. So talk to me if you think this might be useful to you. I just want to mention one thing. The docs for Tracing LLVM include a lot of sort of onboarding info, generic info about how to use LLVM with the GNU toolchain and other things like this, because I expect that PhD students will be looking at it and they might not already know. All right, let's recap just all that. Oh, before I forget, yeah, some future work. Where do we go from there? What I've showed you is basically all of the primitives that are in Tracing LLVM right now. It's not a lot. The first order of business is consolidating that with more tests and implementing something that was in Santwen Vu's PhD thesis that I don't have yet, which is sort of translation validation, like checks between each passes that nothing has broken. There we go. And then some things that I'm interested in is that this set of primitives allow you to better control the way that the compiler compiles the program. And it might not be useful only for security. That's an open question. I like to test that, for instance, for debugging info performance or things like this. The big issue is finding out what kind of security primitives you would have to put in the compiler to write security countermeasures. What's a unifying sort of security language for the compiler that would be useful? That's a big question. All right, so what did I say? I talked about basically just 2 features, opacification and tracing in LLVM. But the underlying message, hopefully, is that these are good foundations for fitting security in a production compiler, which would be exciting. And these are the links again. This will lead you to these slides, which have all the links. And that's it for me. Thank you.
Hello. Thanks for the talk. I have a question about, I think it was on slide 2 in the opacify function from like when you opacified 73 or something. Yeah, right. So do you declare this function as like pure? Like could it have side effects?
Wow. I think there's an entire chapter in my thesis about this. Yeah, so basically you can do a lot of variations, and depending on the variations that you do, you get more or less threats to the correctness. The original function in Santuezu's thesis is pure, and I was a bit spooked by a lot of the problems that you can have with pure functions. There's a bunch of them with completely crazy C code where it breaks. So my version is side effecting, but I think there are situations in which you can use the pure one. I'd like to go into more details and understand this better. But yeah, my knee-jerk reaction is just side effect everything, and then you have more guarantees.
All right, thank you.
So just quickly, just for the tracing,
yes,
can that sometime on its own have overhead? Performance overhead?
Yeah, there could be overhead in missed optimization costs.
Yes.
The big problem is, actually, maybe that's something I could evaluate. One part I didn't mention is the performance cost of all this, because it's really, really, really hard to decouple the performance cost of the opacification and tracing methods from the performance costs of the countermeasures that you implement with it. In this case, yes, the one cost from tracing is going to be the missed optimizations. But you could argue that since the optimizations would have been unsound security-wise, right, you have to decouple the optimizations that you really couldn't do security-wise from the ones that you just didn't do because the formalism didn't allow for them, even though you could have done them. And I don't know how to evaluate that.
To go back to the question about pure, to go back to the pure functions thing. How hard was it to convince LLVM that your opacification operation was non-deterministic? Is it something that is easy to do, or did you have to work for it?
No, it's pretty easy. So if you do side effecting, you have something stronger than non-deterministic. Yeah. And if you don't want non-deterministic, you have other attributes you can put on built-ins that are also relevant. No merge, no split. You can get something equivalent. I don't think there's something that exactly means non-deterministic, but you have equivalent things that are fairly easy to get through. All right.
Okay, let's thank the speaker again.